Universidad Andrés Bello, to tell us about conformal renormalization of scalar-tensor theories. Please, go ahead.
So first of all, I want to thank the organizers for this opportunity. Today, I want to show you the work we did for my master thesis at Universidad-HoLAGrav. I'm currently a PhD student at the Universidad Andrés Bello. And this work was done in collaboration with Ignacio Araya, Joros Anastasio, Cristóbal Corral, and Nelson Merino. So the outline of the talk is the following. First of all, I want to give you some kind of introduction to renormalization and AdS spaces. Then before constructing the procedure of conformal renormalization, I want to give you some brief introduction to conformal gravity. Then we are going to construct this conformal renormalization procedure applied to conformal gravity. Then we are going to apply this for Einstein-AdS with conformally coupled scalar fields, and then to conformal gravity with the scalar fields, and finally the outlook and the future work. So first, we start with general relativity. This theory is described by the Einstein-Hilbert action that in 4 dimensions is described with this action right here. And we want to have a well-defined variational principle, in this case for Dirichlet boundary conditions. And in order to do that, we have the Gibbons-Hawking-York term that is given by this K right here. That is the trace of the extrinsic curvature of the manifold. And we still have the freedom to add boundary terms to the action, as we want this action to vanish in the vacuum. So in this case, we can add this K naught, that is the trace of the extrinsic curvature of the background. Later, I will explain a little more what the background means and why we need this background, this term. As we have this action, we want to calculate the finite Euclidean on-shell action and finite charges. In order to do that, we renormalize these quantities. With renormalization, we mean the cancellation of the divergence. Often we use renormalization with boundary terms, that this includes background subtraction, as I was saying. This method usually we use in flat spaces, but this fails in AdS. We can also do this renormalization procedure with intrinsic and extrinsic boundary terms, but as I will show you later, these also have problems. So we end up with the conformal renormalization. That is the method that I will try to explain in this talk. So we are interested mostly in AdS spaces because of this result, the AdS CFT correspondence that said that in the saddle point approximation, the Euclidean on-shell action of AdS is equal to minus the logarithm of the partition function of the CFT. This is mostly used when we calculate the thermodynamics quantities of the system. So it's a very useful result. And then we have the Einstein-Hilbert action with negative cosmological constant. This is this action right here. We still have the Gibbons-Hawking-York term in order to fix the variational principle. And anti-de Sitter is a maximally symmetric space whose metric can be written in this form. This is the usual way we can see the metric of anti-de Sitter, where the omega square is the metric of the 2 sphere. And this equation right here tells us that, anti-de Sitter has constant curvature. So it's a maximally symmetric space, as I was saying. And this is a solution of the Einstein-AdS equation with negative cosmological constant. That are this equation right here. I want to show you some properties of AdS first. Any asymptotically locally AdS spacetime can be expanded at this form that is known as the Pepperman-Graham expansion, where the spacetime boundary is located at zeta equal to 0. The AdS action that I showed you before has a well-posed variational principle for the G0. However, this action still diverges as the volume of the asymptotically locally AdS spacetime diverges. So as I told you before, we can use sort of background subtraction in ADS, but this method works only for the action. If we try to calculate the conserved charges in some formalism, these charges will be still divergent. So we need another method for renormalizing in ADS that basically does not depend on the background. And so the first I want to show you is holographic renormalization, also known as counterterms with a C. This method uses intrinsic boundary terms of the geometry. The action renormalized is given by the previous ADS action and plus this action of this counterterm series that in 4 dimensions is closed, but in higher dimensions, we cannot find closed form in arbitrary dimension. And also we have no, we don't have a generalization for this action in any generic Lovelock theory. This action is given by this, and we have here the intrinsic curvature that is being defined by this equation. We can use this renormalization method to calculate the Weyl-Subramanian-Krauss charges, that is sort of extension of the Brown-George charges that are used in flat spacetime. In order to do so, we then vary the action. We then have the equation of motion, and this tau mu nu, that is the quasi-local Weyl-Subramanian-Krauss tensor, when we can see that this part will correspond to the Brown-George quasi-local stress tensor, and this part will be the part that renormalize this tensor for ADS. Then, applying the Brown-George formalism, that includes constructing a quasi-local conserved stress tensor, we can find a conserved charge that will be defined as this, where here we can see that sigma is a codimension 2 hypersurface, T is a Killing vector, and U is the normal vector to the sigma hypersurface. Then we can use another boundary term formalism that will be the topological renormalization, also known as counterterms with a K. This formalism is built by with the extrinsic curvature terms of the manifold, and also has a problem when we are in D higher than 4. It fails for renormalizing the spaces with not conformally flat boundaries. As we are working here in 4 dimensions, we don't have that problem. So in D equal to form, the renormalized ADS action will be this, written in the MacDowell-Mansouri form. This is basically the Einstein-AdS plus the Gauss-Bonnet term with a fixed coupling constant, and can be written in this form. And this is useful because for Einstein spacetimes, we can write the Weyl tensor as this form that we can see that is the same as in the parentheses. So on shell, the renormalized action becomes the one of conformal gravity. This is only for Einstein spacetime, and this means that we can embed the solution of Einstein gravity in conformal gravity. So that will be for renormalized method in AdS spacetime. Now I'm going to show you how the conformal renormalization procedure can be constructed. First, why we're interested in conformal gravity? The most important result is that for Einstein, asymptotically locally AdS spacetime, this action is finite, as was shown by Brumel and collaborators in this reference. So we are interested in AdS spacetime, so we're going to use a lot this result. Also, the action of conformal gravity is invariant under this transformation of the metric, and also it is believed that could explain the flat galaxy rotation curves. So the action of conformal gravity is this action given right here, and the equations of motion are back equal to 0, where C and S are the Cotton and Southern tensor defined as this. We can see that if we use the Einstein condition in the equation of motion of conformal gravity, we will get the following, as the Einstein condition means that a constant, the Ricci tensor is a constant times the metric. So if we replace this in this Hausen tensor, we will get something that is proportional to the metric. If we replace this in the cotton tensor, we will get the covariant derivative of the metric, and this is 0. So if we replace this on the back tensor, we will get the back equal to 0. So the equation of motion are satisfied. Then for Einstein spacetime, the action of conformal gravity becomes the one that I'll show you before. That will be F squared, which in turn is equivalent to the holographic renormalization shift just by a constant. So here we can see that there is sort of relation between conformal symmetry, renormalization, and AdS spacetime. So we will get, now I will show you how is the procedure of conformal renormalization is done. First, we will consider Weyl variations of the AdS action, the metric transform as this, and the Ricci scalar as this. Then if we plug this, the total Weyl variation of the Einstein-AdS action will be this. As we can see, this is not Weyl invariant because this is not equal to 0. So we have the freedom to add an extra term or boundary term to make the action on-shell Weyl invariant. Then, for instance, as we were using the Gauss-Bonnet, I will add the Gauss-Bonnet. This is the Weyl variation of the Gauss-Bonnet. And if we sum all the contributions, we will get this, and this is still not Weyl invariant. However, if we evaluate this on Einstein spaces, the action variation will become this, and if we demand on-shell Weyl invariance, we will need this to be 0. So we can fix the C4 as L squared over 4, and then this will be Weyl invariant. And this also corresponds to the action that matches the topological renormalized Einstein-AdS action. That was the action that I showed you before, written in the MacDowell-Mansouri form. That is this. So again, we have some relation between conformal symmetry, renormalization, and AdS spacetime. Now we will apply this with conformal scalar fields, because this is kind of the new result, I think, because conformal renormalization works, but it wasn't proven with conformal scalar fields. So first, we will add scalar fields. These scalar fields are relevant in particle physics, cosmology, and gravitation. And we will have here a non-minimally coupled scalar field, a conformally coupled, that is given by this action, that is the usual action for a conformal scalar field. And now we consider finitesimal Weyl variation of this action, where we know how the metric transform, and this is how the is the Weyl variation of the scalar. Now this action transform as a boundary term, and as we saw before, we can add another boundary term to render this variation finite, but we are taking another route. In this case, we will consider an extension of this conformal invariant scalar tensor that is very useful in this kind of theories, that it was introduced in this reference by Julio Oliva and Ray. So we will have an extension, a sort of shift of this tensor that is given by this, and this is now called sigma tensor. And this tensor has the same conformal weight as the Weyl tensor, and straight is proportional to the Yamabe operator. The procedure that I showed you before, that was just taking the Weyl variations of the action, also works, but if we take the same route for these conformally coupled scalar fields, we will get a problem when the conformal scalar field is constant, because it will break the conformal symmetry. So in this case, it's better to introduce the extended tensor to write a conformal action. So now we will take this square of the sigma tensor, and then if we do some algebra here, and we can see that we'll get the same action for the conformally coupled scalar field plus some counterterms. And of course, the kinetic term is different, but we'll get the same equation of motion for the conformally coupled scalar fields. In this case, this sort of current is given by this equation. And as I was saying, this action gave the same equation of motion as the one of the conformally coupled scalar field. Additionally, we will get sort of free the counterterms that have the conformal symmetry for this action. So we can have a direct application in this for this procedure. So we will take now the Einstein-AdS action with conformally coupled scalar fields. As we saw before, we can write the action for the Einstein-AdS with f squared and the conformally coupled scalar field with sigma squared. This equation of motion are the following. When we will have this T mu nu for the scalar field that is given by this, and the other of this Einstein-AdS equation of motion.
Mairym?
So if we take,
Can I make you a question?
so, yes, sorry.
You have to find G, right? That's the end of the computation.
Sorry?
You have to find G. I mean, in the previous slide, you wrote the action and you have the G there.
Oh, G is the Gauss-Bonnet. Sorry,
Is the
I
Gauss-Bonnet
should
term?
say that.
Okay.
It's the Gauss-Bonnet term. Sorry.
Perfect. Thank
Yes. I don't think I should write that. Thanks, Oscar. So I was here. So these are the equation of motion of the action. And then if we take into account this equation of motion, we can write the action on shell of this action right here when we have Weyl square term and some term proportional to the traceless Ricci term, that for Einstein spaces, we know that this tensor is 0. So we will get the part only for the Weyl tensor that we know that if we evaluate on AdS spacetimes, this part will be finite. And then the whole action will be finite. Some example that is not Einstein is the Martinez-Staforelli-Troncoso-Zanelli black hole that we'll find considering a spherically symmetric line element, where this sigma square is the line element of a two-dimensional base manifold sorry, with constant curvature k. In order to have a black hole, we set k equal to -1, and the solution of the previous equation of motion is asymptotically locally AdS and are given by this metric function, and this for the scalar field. Well, in order to have the black hole, we will need this condition in the parameters. As I was saying, this solution is not Einstein, but have a Weyl falloff, so it's finite. Due to the terms are falling apart 1/r. We can get the Hawking temperature for this black hole that is given by this, and also using the Einstein, the Euclidean shell action is equal to minus the logarithm of the partition function. We will get the renormalized Euclidean shell action, and it's given by this, where sorry, I have a cold, where omega is the volume of this this right here, that it tells us that all the points of the hyperboloid are identified.
Mairym, what is sorry, what is H?
Yeah.
H mu nu that you're writing there? I couldn't.
H is the traceless Ricci tensor. When we
okay.
When you decompose on the independence components of the Riemann tensor, you have this part that is the partial trace of the Ricci tensor.
Okay, thank you.
You're welcome. So this is a first example. And now we can also apply this procedure for conformal gravity with scalar fields. We already know that conformal gravity is finite for asymptotically locally, ADS space. So now the only part that we have to complete conformally will be the part of the scalar sector, but we also did that. So the action now will be Weyl square minus zeta with sigma square. And these are the corresponding equation of motion, with this corresponding to conformal gravity, and this for the conformally coupled scalar fields. And now we can use a useful decomposition of the Weyl tensor in order to, again, write the action in a more familiar way. This on shell will be this action, where again, we have the Weyl square and some contributions now proportional to the T mu nu. If it's the case where T mu nu is equal to 0, we again have Weyl square, and again, we know that Weyl square is finite for asymptotically locally ADS space. Entonces, so we will have the quantity is finite. For a constant scalar field,
Mairym? Julio here.
Yes.
So the T mu nu there is the T mu nu of the standard conformally coupled scalar field.
Yes.
What's the T mu nu? Yeah, okay, perfect. Thank
you. Is this T mu nu. So for a constant scalar field, these field equations admit an Einstein spaces as solutions, since as I showed it before, they are back flat and has vanishing stress tensor. And also we can consider another type of solution that are stealth solution, sorry, that is the case right here. Stealth are not trivial configuration with vanishing T mu nu. So if we consider a stealth over the Rieger metric, that is the most general metric solution for conformal gravity, so we replace this static again static and spherically symmetric in the equation of motion of the action, then we will get the following solutions. These are the solution for the metric function and the scalar field, when we will see that these solutions only exist for nu different than 0 and are not, again, different than 0. Here, again, we can find the Hawking temperature of the previous solution using the Hawking temperature is the inverse of the period of the Euclidean time. And the Euclidean on-shell action we can find, again, given by this expression. And we can notice some important things right here, that even though the scalar field does not backreact, that means that its T mu nu is equal to 0, because that's the definition of a stealth solution. It presence modifies the Euclidean on-shell action in a non-trivial way, because their integration constants are present in the Euclidean on-shell action. So now we're giving some conclusion and the future work. We have shown that this procedure, conformal renormalization, that previously was shown that it works for metric degrees of freedom, now also can be extended to theories that consider scalar fields. That means degrees of freedom beyond the metric ones. This is done by restoring the Weyl conformal invariance of the action, and this will dictate the counterterms that render the action finite and give us the conformal symmetry of the whole action. Also, this method of conformal renormalization with the scalar field is currently being studied in D equal to 6 by Ignacio, Yorgos, and other collaborators. And the previous solution, we have a lot to study right there. We have, we can see that if it exists some Hawking phase transition between them, and also conformal renormalization of conserved charge of asymptotically local in ADS works for scalar-tensor theories. And I think that's it. Thank you.
Okay, thank you very much for the great talk.